This is question 1, homework 10, question 1. So from the lecture notes, collect the definitions and the simple properties of statistic process. So for the first one, Poisson process, the number and t of the points ti in the interval t1 t2 between the interval between t1 and t2. So the length t equal to t2 minus t1 is a Poisson random variable with parameter lambda t. So the probability of n t1 t2 equal to k is equal to e to power negative lambda t times lambda t to power k over k after intervals t1 t2 and t3 t4 are non-overlapping. Then the random variables and t1 t2 and t3 t4 are independent. At a time moment t, there is no more than one Poisson point. Using the points ti, we form the statistic process xt equal to n 0 to t 0t. The first order probability is masses probability xt equal to k equal to e to power negative lambda t to power lambda t to power k over k, and the mean value is expected value of xt is equal to lambda times t. Autocorrelation RT1 T2 is equal to lambda squared T1 T2 plus lambda mean of T1 T2. Autocovariance is autocovariance T1 T2 is equal to lambda squared T1 T2 plus lambda mean T1 T2 minus lambda T1 times lambda T2 equal to lambda mean T1 T2. The mean of Poisson process is lambda t, which is a linear function of t. It matches our common sense. Longer time we wait for the expected number of buses larger. The autocorrelation function contains a term mean t1 t2, which comes from the property of independent increments. Question 2. Problem 2 is Poisson increment process is defined as yt equal to xt plus epsilon minus t over epsilon. First order property masses is probability yt equal to n over epsilon equal to e to power negative lambda epsilon times lambda epsilon to power n over n factor t. Expect value of yt is equal to lambda. Autocorrelation RT1 T2 is equal to lambda squared when absolute value T1 minus T2 is greater or equal to epsilon, or lambda squared plus lambda over epsilon minus lambda times absolute value T1 minus T2 over epsilon squared when T1 minus absolute value of T1 minus T2 less than epsilon. Autocovariance of T1 T2 is equal to 0 when T1 minus T2 greater or equal to epsilon. Epsilon over lambda over epsilon minus lambda times absolute value t1 minus t2 over epsilon square 1 absolute value t1 minus t2 is less than epsilon. The Poisson increment process is introduced to prepare us to define Poisson impulse process, one way to define. It is interesting to see that in the expression of autocorrelation, lambda over epsilon minus lambda times absolute value t1 minus t2 over epsilon square. So when absolute value t1 minus t2 is less than epsilon, is a triangle with area lambda, which is independent of epsilon. When epsilon goes to 0, the triangle becomes an impulse with area lambda. Question 3. Point impulse process is defined as zt equal to derivative of xt over derivative of t, where xt is the Poisson process. Probability of masses, since it's a point, so it's no definition for that. And for the mean, the expected value of zt is equal to lambda. The autocorrelation t1 t2 is equal to lambda square plus lambda t1 minus t2. Zeta autocovariance correlation t1 t2 equal to lambda zeta t1 minus t2. The process zt minus lambda has 0 mean, and autocorrelation t1 t2 equal to lambda sigma t1 t2. That is zt minus lambda is white noise. In the real world, there are some short noises as in the figure. Question 4. Semi-random telegraph signal xt is defined based on the Poisson points again. The number t1 t2 of the points ti in the interval t1 t2 of length t equal to t2 minus t1 is the Poisson random variable with parameter lambda t. Probability of t1 t2 is equal to k equal to e to power negative lambda t. Lambda t times lambda t to power k over k factorial. Xt equal to 1 k is even in 0 and t. Xt equal to negative 1 k is odd in 0 and t. First order probability methods. Probability xt equal to 1 is equal to e to power negative lambda t, e to power lambda t plus e to power negative lambda t over 2. Probability of xt equal to negative 1 equal to e to power negative lambda t times e to lambda t minus e to power negative lambda t over 2. The mean is expected value xt is equal to e to power negative 2 lambda t. Autocorrelation is t1 t2 equal to e to power negative 2 lambda times absolute t1 minus t2. Autocovariance is equal to e to power negative 2 lambda times absolute value t1 minus t2 minus e to power negative 2 lambda T1 plus T2. The P probability xt equal to 1 is not 1/2 because we start with positive 1. The probability of xt equal to 1 should be a little higher than 1/2. Probability xt equal to 1 equal to e to power negative lambda t times e to power lambda t plus e to power lambda t. The question 5, random telegraph signal yt equal to a times xt. Probability a equal to 1 equal to p. Probability a equal to negative 1 equal to 1/2. The first order probability method is p. Probability of yt is equal to 1 equal to probability yt equal to negative 1 equal to 1/2. The mean of that is equal to 0, and the autocorrelations is e to power negative 2 lambda times absolute value t1 minus t2. The autocovariance is the same. Question 6, random walk. Toss a fair cone n times k as the number of heads in n tosses. X and t equal to ks minus n minus k times s is equal to z k minus t times s. The first order probability method is probability of xt equal to x and t equal to rs is equal to combination of choose n from n plus r divided by 2 times 2 to power 1/2 to the power n for nt less than t less than n plus 1 times t. The mean value is equal to 0. The autocorrelation is equal to the mean of n or m times s squared. The autocovariance is the same. The question 7, Werner process. Wt is equal to limitation rt approach 0, the s squared over t approach a, and n approach infinity, xt, where xt is a random walk. The first order is Wt is equal to 1 over square root 2 pi alpha t times e to power negative w squared over 2 alpha t. The mean is equal to 0. And the autocorrelation is also the mean of t1 t2 times alpha. The autocovariance is same as the mean value of t1 t2 times alpha.